What if a pistol did not push a bullet with chamber pressure, but launched a tiny rocket that accelerated after leaving the barrel? In 1965, MB Associates tried to sell the Gyrojet as the future of handguns. The promise sounded impossible: almost no recoil, no empty case to eject, a lightweight launcher, and a projectile carrying its own engine. But that futuristic idea created its fatal weakness. At the muzzle, the Gyrojet was not powerful. It was still waking up. To understand why it failed, we need to dissect the rocket, the ignition system, and the physics of slow acceleration. The Gyrojet came out of the American aerospace imagination of the early Cold War. Robert Mainhard and Arthur Beale formed MB Associates in California, then worked with engineers such as Matthew Hengel on hand weapons that could launch miniature ballistic rockets. Their key hand weapon patent was filed in 1962 and issued in 1965. The familiar production collector example became the Mark I Model B, a smoothbore rocket handgun with 6 rounds in the grip and a silhouette that vaguely echoed the M1911. For a brief moment, it looked like science fiction had entered the display case. But regulation, manufacturing cost, and inconsistent ammunition quickly narrowed the dream. The original 13mm bore sat just above the half-inch threshold that mattered under United States firearms law, while later 12mm versions could not fix the deeper mechanical problem. Mechanically, the Gyrojet reverses many assumptions of a normal pistol. In a conventional cartridge, the firing pin strikes the rear primer, gas pressure expands inside a strong chamber, and the bullet is forced down a rifled barrel. In the Gyrojet, the projectile itself is the pressure vessel. The hammer does not simply hit a rear primer. It impacts the nose of the rocket, driving the round backward against a fixed firing pin in the breech face. For a fraction of a second, the hammer also acts like a restraining mass, holding the rocket back until thrust becomes more uniform. Then the rocket pushes past the hammer and travels through a smooth launch tube. This is clever, because the launcher does not need to contain a violent chamber explosion. It is also fragile, because ignition timing now controls everything. The projectile is the heart of the system. A Gyrojet round is not a bullet sitting in a brass case. It is a tiny solid fuel rocket. The base contains angled exhaust ports that spin the projectile as hot gas escapes rearward. That spin replaces conventional rifling, because there is not enough initial pressure to force the projectile into grooves. The trade-off is brutal. A normal handgun projectile reaches peak speed inside the barrel. The Gyrojet starts slowly, then accelerates in open air as its propellant continues burning. Period accounts and later museum descriptions often place maximum velocity roughly 50 to 60 feet from the muzzle, at around 1200 feet per second. That means the weapon is weakest at exactly the distance where most pistols are expected to be most dependable, immediately in front of the muzzle. The Gyrojet did not fail because the idea was boring. It failed because every shot depended on a tiny rocket motor being manufactured with near-perfect consistency. If one exhaust port varied slightly, the thrust vector changed. If propellant condition or ignition timing varied, ignition could become unreliable. If launch timing or nozzle alignment drifted, accuracy suffered. Instead of a clean ballistic line, accounts describe early arrangements that could corkscrew, wander, or print wide groups. There was also a human problem. Loading and chambering felt counterintuitive compared with ordinary handguns. The ammunition was expensive, specialized, and difficult to produce at scale. The pistol had nearly no recoil, but it bought that advantage by moving the most complicated engineering from the gun into every single round. MB Associates did not stop with one pistol. The Gyrojet family included carbines, presentation models, experimental survival concepts, and later 12mm versions. Some examples were marketed to collectors, others were explored for military or rescue roles. The design was appealing because a rocket launcher could be light, simple, and almost recoil-free. The same rocket launcher idea also showed up in specialty signaling and survival concepts. In practice, the system became squeezed from both sides. The law treated bore diameter over 1/2 inch very differently, making the early 13mm concept a regulatory headache. Meanwhile, shrinking the bore did not make the miniature rocket easier to mass-produce. Smaller parts demanded tighter tolerances, and tighter tolerances made the ammunition even more expensive. The Gyrojet remains important because it exposes a timeless engineering trade-off. You can simplify one part of a system by moving complexity somewhere else. The pistol body became light and simple, but the ammunition became a precision rocket engine. That is a dangerous bargain for any weapon meant to be affordable, reliable, and repeatable. Modern manufacturing, better propellants, and computer quality control would certainly improve the concept. But they would not erase the central physics. A rocket projectile needs distance to accelerate, and a handgun is often judged by what happens at very short range. The Gyrojet was not merely a failed gadget. It was a real experiment that asked whether the bullet itself could become the machine. The Gyrojet rocket pistol was a brilliant wrong turn. It reduced recoil and moved case ejection and chamber pressure stress out of the launcher, but only by demanding that every projectile behave like a perfect miniature engine. That made it futuristic, collectible, and fascinating, but not dependable enough to replace the ordinary pistol. Which strange weapon should we dissect next? Leave your suggestion below, subscribe, and see you in the next breakdown.